Thank you, Doctor. Thank you for this invitation and all of attendants for the interest in my work, in all work, but because like Doctor said before, we are doing microalgal environmental biotechnology from year from now, and working with Dr. Siva Subramanian in an alliance. So I will begin my presentation. I will try to be not make you bored, but the point is, I don't know how to. Okay, in a minute.
Yes, sir. And one more thing, I just wanted to add about Dr. Jaime. He is the collaborator of Dr. Subramanian, sir, for the past more than 5 years, right, sir? Or
yeah, from 2013.
Yeah.
Also, like you can see in this slide, we made a joint venture agreement from 2013, and then we created a Phycore company, which is a startup here in Colombia that has been doing environmental biotechnology in the field. So I will try to show you some of the results that we get here, because Dr. Siva Subramanian has his own results in India. But here in Colombia, this microalgal application had been very successful. So let me talk to you about yeah.
Proceed, sir. You may present now, sir. Yes.
Thank you. So I will talk to you about the wastewater, domestic wastewater management. That is the topic that is like in our goal of work right now. As you already know, the typical composition of domestic wastewater is full of many nutrients and pollutants, but almost the main contaminants have nitrogen, and that is mainly in the form of ammonia. But also you have organic load that is expressed in the form of biological oxygen demand or biochemical oxygen demand. The point is, usually across the history, the wastewater was treated in 3 steps, and usually microalgae was like in the 3rd step, just like a tertiary treatment just for nutrient removal. And what we know for our work is that that's not true, that you can perform a total wastewater treatment using microalgae, but still today is kind of difficult to convince people to that, because the normal or the regular understanding is that you have the primary treatment that we already need, because the solids you can remove with microalgae, but you have to have a secondary treatment of bacteria or something like that, or chemical, and only in the tertiary part you can use microalgae. But we already know that that's not true. Microalgae have much more power to decontaminate water. So today we really find many publications, many work about microalgae and the treatment of domiciliary wastewater, which is the most abundant wastewater around the world. You know, this is a huge quantity of wastewater that we produce from our cities and towns. So many works from now, like all public publications, have a lot of evidence that the microalgae can remove not only organic load and nutrient, but other heavy contaminants that you can find in the water, including the pathogens. I mean, the other microorganisms that are generate illness in human, you can remove with microalgae, and that's a very good situation, and we can take advantage of that to create new systems. But additionally, what we know right now is that it's not just the microalgae. Microalgae is like the very basis of a microcosmos that is confirmed also for bacteria and fungi. And in the case of bacteria, there is a lot of work recently explaining this very simplified model. I have to say, it doesn't look like that, but it's a very simplified model of the interaction between bacteria and microalgae, that according to the moment, light or darkness is different, and that allows that to use the microalgae and this environment to focus in more than one decontamination target. And I'm sitting that my friend Dr. Shiva Subramanian. But the point is, the algae produce or generates some situation that can be beneficial for the bacteria or not. And this is, for example, the microalgae increase the pH, increase the oxygen concentration in the media, and can produce some bacterial inhibitory growing substances. But also, the microalgae release many substances that are good for some bacteria, not for every bacteria, but for some bacteria. And there is enough evidence today that there is some cases in which bacteria alone or microalgae alone can deplete, can remove some kind of pollutants, but when they are together, they achieve it. In my own thesis of my PhD, I have an example of that, and I will talk about that later. The point is, you have to choose the microalgae that you will use in a process of decontamination of water. Not all microalgae are good for that. And then you are looking for some photosynthetics, mesotrophic and strong organism that can work in difficult conditions. That microalgae have to have a high growth rate because you have to compete with other microorganisms like anaerobic ones, and that microalgae have to have a nutrient uptake rate high. And that's because otherwise you will have a long rotation time in the reactors. And then if you have to treat a large amount of water, you will have to construct very big tanks, and that's no good because it will make the process not sustainable. The point is, we prefer to use green algae because the wall is like an armor that give strong to the microalgae against the toxics. Domestic wastewater have a lot of change in concentration of nutrients and pollutants, and also have toxic pulses. That means that in some moments, some very toxic substances are high concentrated in the water. And then we find that these chlorophytes have a good resistance against this. You have here one of the consortia of many microalgae that I actually use to decontaminate petrochemical water. And you can see that are chlorophytes. My favorite one is this, Cyanidesmus dimorphus, and it's the microalgae which I am working right now in my thesis. But the point is, this microalgae take control of the consortia. At the end of the process, was more Cyanidesmus dimorphus than any other of the microalgae in the culture, in the reactors. And then that was the reason why I take out to the lab and I try to find why that microalgae prospers so well in that water with petrochemical pollutants. I have the idea that maybe this microalgae could use the phenol or other hydrocarbon like food, but was not so simple. Well, other thing that you have to take in account to use microalgae to treat domestic wastewater is the phases of microalgal growth. Is in the optimal condition, you will know how much time take the exponential phase, how much time take the stationary phase, and when your culture will begin to die. So you will go with your culture until this point, and then only then you will begin the process of the contamination in your reactor. I mean, you will begin to add the effluent with the pollutants, and then you will sustain the process until this point. And in this point is supposed to you have a re-inoculation process, which means that you will take new biomass that is not tired with the pollutant. In a process, in a plant, you can do this with recirculation of your biomass. Then you recover the biomass at the end of the process, and then you will put that biomass resting with nutrients without contact with the pollutant, and then you will put back in the reactor. And this is very easy to achieve if you know your consortia of your microalgae. not so easy when your consortia is changing. And we use this methodology. This is very simple to start up any of processes. It's important to say that we always use local microalgae. We don't transfer microalgae from one zone of the country to other. We go to the place where we will work, and we will find the microalgae in that place to try to do the bioremediation, the phycoremediation with that microalgae. So we take samples and we go to the lab. We usually use 3 types, at least, different types of culture media, and trying to recover a broad number of species of microalgae. And then we do at the lab a tolerance test, which means to culture the microalgae with the pollutant, with the effluent, with the real effluent that we will confront. And then some of them will die, some of them will survive, and that will be like the selected group of microalgae. We also cross the information with the we already have in the papers, in the literature, a lot of information about which species is good for which kind of pollutant. So then we scale up the culture of selected microalgae, usually at the lab until 20-30 liters, and then we go to the field, and then we have these 4 kL usually tanks in order to inoculate the tanks and begin the process of warming up the microalgae, the consortia. So you can see here in this photo, we have like 4 or 5 tanks, 4 kL each one, and we begin the process in the first one. We inoculate with 3 liters, 1 kL of water, fresh water, and then we begin to add same volume of effluent. And then we recirculate that until we get a good cellularity, could be like 120, 150 cells per milliliter, and then we add more effluent. When we reach the full volume of the first tank, then we take the half of the volume and go to the second tank, and then we add another half volume of effluent. And then we continue until we reach again the cellularity, and at the end we will have all the tanks full, and then we begin to recirculate the volume of all the tanks and adding constantly effluent. And that's like the main process. But we can do this because microalgae can remove many nutrients from water. I will be very fast here because I know we all work with microalgae and we understand this like very easy, you know. But the point is, microalgae can fix for example, the carbon from the atmosphere or the flue gas from combustion process and motors and engines. Still, the cell can use the carbon like carbonates for cell growth, and can take it for direct uptake or conversion of carbonate to free carbon dioxide through a carbohydrate activity. You know, if you have low pH in the media in these reactors, for example, you know, you will have a carbon uptake by simple diffusion. But if you have media over than 7, then you will have bicarbonate, and then it will activate some external carbonic anhydrases and promote the active transport inside the cells. So when you try to capture carbon, for example, it's useful that you perform that in a air-leaf reactor. Is this kind of reactor that is supposed that induce more contact between every cell with the gas and favor the intake. But you also will have to check the pH to don't get over 7 in order to make more easy to the cell take the carbon. And when we talk about nitrogen, and I will talk only now carbon, nitrogen, and phosphorus, and I'm sure that you already know why I will talk about nitrogen and phosphorus. The point is, microalgae actually, and all eukaryotic algae, play a key role in the conversion of this inorganic nitrogen in the organic form through a process that is called assimilation. You can see here, there is several enzymes that mediate that process, you know? And this is very important. Microalgae tend to prefer ammonium over nitrate. And nitrate consumption usually doesn't occur until ammonium is almost completely consumed. And this is important because in our culture medias, not always the nitrogen is in form of ammonium. And you will see why this is an important thing in the practical of the biotechnology, environmental biotechnology. Phosphorus, in this case, the nutrient enters microalgal cells through active transport. You can see here that the microalgae express in the surface proteins that transport the phosphorus inside the cell. So the point is, this intake, this phosphorus consumption depends of the availability and the concentration of the phosphorus in the media. The point is, when the phosphorus is too high in the media, the cell express a different type of transporter that have low affinity to the phosphorus, and much number of these transporter, but with low affinity. And in the opposite case, when the phosphorus is too low in the media, they will express another kind of transporter that will have a more affinity. Even the transporter itself is less present in the media. So there is a lot of ways in which the cell can intake the phosphorus, but also like a storage inside the cell, or use it directly in the production of this kind of molecules that usually are like energy related molecules. So give me a minute. There is important factors that we have to take in account when we are using microalgae for effluent treatment. And usually we talk about the initial nutrient concentration, the light intensity, obviously the pH, the temperature, but also the density of cells in the media. However, among all these factors, the nutrient concentration and the nutrient relation with the light intensity are the more important for the microalgae removal of pollutants. Basically, I'm talking about the MP radio. I'm sure that you all have heard about the MP radio, about the Redfield proportion, which means that the cells react different when the nitrogen and the phosphorus concentration in the media are different, you know? So let's go directly to the point that there was a radio, optimal radio, that was called the Redfield proportion. It was 16:1 MP, nitrogen phosphorus. And it's supposed to be like an average value in which most of the cells feels okay and uptake both nutrient and others in a very, very efficient way. However, if we compare, I mean, in this graphic, you can see that the broad green line is that MP radio, 16:1. And the other lines, the other green lines, are the limits of the corrected MP radio from the Redfield ratio, that was like 22:1, and that was a result of a more big study across the ocean. But if you can see here, different species of microalgae have different ideal MP radius. So how you do when you are working with a consortium. And even more important, if you see here the circle, the red circle, the red triangle are representing our usual culture media. And then the MP radius of this culture media are far away from the supposedly be optimal NP ratio. And also the wastewater and the usual effluent have different kind of NP radios. So when you have a culture and you are trying to decontaminate water with that culture, you have to take in count this, because probably your culture is not working very well because the NP radio of the real effluent are not like the optimal for your species. And then you have to add substance or change the way in you recirculate the tanks in order to correct that. But it's even more complex, because one thing is the total nitrogen and phosphorus that you can check in the media. Another thing is the bioavailability of that for the cells. It's not the same. Then you will have to take that in count, because your calculation could change about the NP radio. And the last comment that I will say about this is this one. Look here, then you have a graphic that shows how the nitrogen tends to be present in different medias. And then you have here, for example, or one of the best culture medias. And then you have here in this green as the triangle, the usual wastewater and effluent presentation of nitrogen. So what I'm showing you this because we used to make the lab test of consortia of species of bioremediation with our culture medias. And for example, for these two, the nitrogen tend to be organic in that preparation. But the wastewater, most of wastewater have to have ammonia. Like I said before, usually the domiciliary wastewater have ammonia. So you can test a consortia or at a species to bioremediate something, and then when you go to the field, then you find that this is not working. And it's because, like I said, there is a different type of nitrogen molecule in the media. So nothing is better than the real wastewater to make the lab test. And I really recommend to transport a good amount of that wastewater to your lab before you release your chosen consortia, because nothing is better to try with the real wastewater. The other medias are not so good to determine if the consortia will work. So using microalgae consortia for phycoremediation, for remediate wastewater, have advantage and limitation. But we really think that the advantages are more than the limitations. And we have found that these limitations, at least that are pointed by Goncalves, are like very well handled when you use a good consortia, not one species culture for remediation. This is also, you already know about the advantage of phycoremediation of other system, like doesn't use chemical to correct the pH, like achieve a greater reduction of the organic load, like reduce the smell. That's a very important thing, and a very like successful reason for our process here in Colombia, that the smell is no bad, you know, and other obviously not a sludge formation, you know. But at the end, there is another reason. This is less expensive. In any case, if you compare the cubic meter processed with phycoremediation compared with other technologies that are very present in the market, phycoremediation is less expensive. And this is a very important thing, because we every day produce more and more wastewater. So we need something cheap and effective. So say that, let's go to our successful cases. In this case of a bioaugmentation with a microalgal predominant microbial consortium. This is a expression that we are introducing because we understand that this is not just microalgal consortia, and this is very important. The point is, microalgae consortia compared with microalgae bacteria consortia, the evidence shows that the microalgae bacteria consortia is stronger and can allow to make changes in the effluent without crackdown. In most of the works that you can find recently, I mean, 7 years, 10 years from now, in the literature, we talk about half consortia with a large number of microalgae species, but also with the presence of bacteria and fungi. And that's extremely important, we find, for the success of the processes and the sustainability of the process. And this is our first case of a study. This is a swamp at the north of Colombia. This is a swamp, it's kind of small swamp, like 7 hectares. And this is the Caribbean Sea. So this is the north of Colombia, near at the city where I grow up. This is a city of Barranquilla. Dr. Silva Subramanian knows Barranquilla very well. It's very similar to Chennai. Have 3 million people living in Barranquilla. And we are, I mean, this is the Magdalena River. This is the largest river in Colombia. So this is Mallorquin swamp, was supposed to be a swamp, very beautiful, in which people fish for substances. But the problem is, and you can see this red line, this is the León stream, it's Lion stream in English. And León stream was very happy stream until the people of Barranquilla decided to build a wastewater treatment plant. You can see in this photo, but at the south. And that wastewater treatment plant discharged like 300 liters per second of supposedly treated wastewater, but it's not well treated. So the point is that the Mallorquin swamp get ugly, and something was happening. Then the environmental authority called us. We go to Mallorquin swamp and we made samples about the pollutants levels here in this one, inside the stream, and in all green circles that you see across the swamp. One of the things that we want to find with this study was if real, I mean, like to demonstrate that there was the stream which was contributing with the pollution to the swamp, because there is people in Barranquilla to say that was the Magdalena River that have some communication with the swamp, and also because here in this space used to be a garbage deposit, and they say that the garbage deposit drains organic substance to the swamp, and that was not the León stream. One of the main interesting, I mean, the people that say more that was not the León stream was the people that operate the wastewater treatment plant. So we check and we find that the León stream have a level of organic load expressed in biological oxygen demand that was from 120, 150. So it's extremely high, supposed to be less than 10, you know. And then when we check here in this point, near to the mouth of the stream, we find over 700 of organic load. I mean, it was extremely polluted swamp because of the presence of this stream that was coming with the water from the wastewater treatment plant. The point is, we also find that the levels of organic load was decreasing when you get far away from the mold, and that dilution pattern demonstrate that the stream the origin of this problem of pollution of the swamp. So we also take samples of microalgae in our first sampling, and we decide that we will inoculate the consortia of microalgae that we selected in this point after the sampling point, and the movement of water will take the microalgae to the swamp. Honestly, at the beginning, we think that the decontamination effect, if we find some decontamination effect, we will be just in these 2 points, because we say like the swamp is too big to decontaminate all. However, when we we biomentate the microalgae that we find in the swamp and in this riceways, and we fill one of these trucks every 3 days. We fill totally the truck, and we go to this bridge, and we put the inoculum, the concentrate for microalgae, and at the swamp. And the result was good. I mean, this was the first sampling, and you can see this is the stream, and this is the 9 points inside the swamp, and you can find how it was highly polluted. And then we, in this green line, we begin the process of adding the microalgae, the consortia, and then when we do a week after, we do another sampling, and we find that the level was slightly decreased. At the swamp, at the stream was even higher. So at this moment, the stream was putting more organic load inside the swamp. But when we do the third sampling, you can see the effect. I mean, I think it's very, very visual. So we have a 98.3% removal of the organic load. And that was in all the swamp, not just in the mouth of the stream, how we think was in all the swamp, and sustained over all the process of inoculation of the microalgae. We also make studies about the phytoplankton in order to try to establish if our process was inducing any change in the ecology of the swamp, and was not. And this is the formidable of these processes, that you can get the decontamination without altering the normal ecosystem that you have there. Also, the harmful bacteria like E. coli was almost disappear from the water, which is very good thing, because it's water that are usually used for the people living near to the swamp. A minute. So we have that success, and the news goes across Colombia. Then we reach the goal. Then we have this case of another swamp, but a bigger one. You can see here is an enormous swamp. And this blue line is Arroyo Grande de Corozal, like Corozal Grande stream. And this stream received not 1, 5 towns, residential effluent, and in this case, without any treatment. So the stream was extremely poor condition when we arrived, with a bad smell. I mean, like, it's awful case. So we take, again, a consortium of local microalgae, we expose to the pollutant, and we select our team, Then we put in our reactors in the riceways, and we reach levels enough cellularity, and then we begin to inoculate to the stream. In this case, because the swamp was bigger and the pollution case was totally worse, we design and we calculate that we have to put more inoculum in the stream to obtain some kind of result. And then we begin. This is the riceways. This is us with Dr. Shiva. And one of the things that I didn't say is that in this case, we begin to take, we put an amount of inoculum in the stream, and we take polluted water from the stream, and we come back with that water to our plant. And we was using that amount of water to train or consortia in the main tanks. And then when we come back with the consortia was already used to the pollutants, But like I said before, this plant produced more than 10,000 gallons per day. Why? Because the case was worse. So we need to use this car for inoculation with this tractor, with this machine, because the rows are not good for regular cars, and we put the solution here, and then that allows us to obtain good results. And even we get, this project is called Phycosphere, because sucre is the state, and Phyco, well, you already know why Phyco. The point is, we won the best, the first place in Latin America Verde, it's like Green Latin America, prizes of environmental projects. We get the first place, like best environmental project in the year of all the continent, because this project. So we are very proud of that. And well, finally, I have to say that at the moment when the coronavirus begins, we have achieved reduced 50% of the organic load in all the swamp. That is an enormous swamp. And we achieved to decrease more than 80% of harmful bacteria, which is very important for human health, because like in other case, people use that water. So unfortunately, coronavirus invade us, and we have to stop, and we are trying to finish the project right now. The third case that I want to present to you is a case of different case. In this case, was not the pollution that called us in the site, was the cyanobacterial bloom. This is a reservoir. This is the Guajaro Reservoir. It's like an artificial reservoir that was in the state of Atlántico, north of Colombia, also tropical zone, very warm. The point was that there is a very agricultural activities around the reservoir, and suddenly appears like some cows dies, and some cows dies apparently because they drink the water that was in the border of the reservoir. So the environmental authority go to this place and say, like, this is cyanobacteria, but was like observation, was not like proof of that. So they call us and they say us, well, we want to first of all prove that this is cyanobacteria caused problem. I mean that the cows was killed because the cyanotoxins. And also, maybe you have a solution for this, because we hear that you decontaminate the Mallorquin swamp. So can you do something for this? So we decided that yes, we can try to do something for this in a quickly way. And the solution that we proposed was to inoculate a consortia of chlorophytes, to try to, that consortia, make a competitive inhibition of the cyanobacteria in the place. And we also promise, and already do, to detect the cyanotoxins with ELISA test, because there was never like a objective proof. So there was cyanobacteria, even like the appearance of the water and everything was like very clear that was a bloom. So we go, we take the Van Dorn bottle and we sample, we make the analysis at the lab, and we really find that first there was an incredible dominance of cyanobacteria. Microcystis was like the king or the queen, I don't know, of the place, and the microalgae was reduced to 13 species that we can find, you know. And also with that sample we analyze in the ELISA, and we find the cyanotoxins. Microcystin was the main cyanotoxin. So we made the identification and selection about the species that we find, and then we bioaugment the species in other kind of plants, but have the same principle to try to increase the cellularity of the species that we believe that was good for that reservoir. And then we go and we inoculate. In this case, same trucks, but the point was we have to use a boat in order to put the inoculum far away from the border to the current and the movement of the water, move the microalgae, the chlorophytes, to the zone that was affected with the bloom. And was successful. We find very good results in this. One, decrease of cyanobacterial density. You can find here, this is the density of class 1 Cyanophyceae, and then you have the level we find at the beginning of the study. Then we begin the inoculation with 5 species of chlorophytes, and the second sampling, there was half of the quantity that we find at the beginning, and the third sampling, there was less than 10% of the density of Cyanophyceae type 1. And when you see Cyanophyceae type 2, it's even more dramatic, the effect. I mean, there was almost nothing at the third time. So it was very good results in order to remove the cyanobacteria without using any chemical, any other treatment, and very cheap treatment, actually. So in the second monitoring, second sampling, you have 53, 34, 6% of removal, but at the third sampling, in the third sampling station, we have more than 80%. In each case, in this case, 100% of remotion of cyanobacteria using just chlorophytes. The second result, and I find this even more beautiful, is the increases phytoplankton biodiversity. We biomediate with 5 species, but we find 11 species at the beginning of the study and a lot of cyanobacteria. And then we inoculate, and the second sampling, we find 29 species. So we just use 5. So this is the point. The more chlorophyte you put in the water, and then they compete with the cyanobacteria, and they create an adequate environment in order to all the chlorophyte that was already there, but you can't find it with the sampling process because they are too few. But with the environment conditions change, well, they rise. And at the third sampling, we find 33 species, which is more similar to a healthy ecosystem in a reservoir like this. So then you have the micrographies of the first sampling, just 11 species. This is one from the second sampling. Oh, sorry. 11, 33, second sampling. And no, what is happening? Sorry. Well, it's like I have a slide lost. But the point is 11 go to 33 species, which is, you can say, like a restoration of the health of the ecosystem. Just using microG. We don't put any gram of chemical in that bloom. Was every totally natural process. So let's talk about our innovation quickly. We are taking all this knowledge that we find, and we design 3 reactors actually, but I can only talk about 2. This is first one is the BF+2. It's an open closet. You can use in 2 configuration, photobioreactor, and this an induction biofilm induction bioreactor, which means that this structure, that is fractal design structures, sustain between a support platform for the formation of a stable biofilm. And also the reactor induces a flux that is also laminar, almost laminar, sorry, and that flow generates a very, very healthy biofilm. Let me show here a little more. These are the structures that are inside the reactor. And these structures, like you can see, are like slightly inclined, and the almost laminar flow of the water goes over this side, and then there is a biofilm forming there, very, very, very stable biofilm. But the other thing is that this reactor have these lights, LED lights, in the top of the structure, like you see here, the green lines. And the other side of this film, you have like a kind of formation with the same material that is translucent, in which we circulate clean water, transparent one. So when the lights at the top of this structure inside the light over the clean water transmit the light to the bottom of the tank. But the point is, in a decreasing gradient, because the light is not perfect transmitter of the water is not a perfect transmitter of the light. So the micro G, since the micro G circulate from the bottom of one part of the tank to the top of the other, next other, and go down again over the surface, they have like a decreasing light gradient, you know, very, very kind. So we circulate the micro G from all the 4 quadrants several times in an hour, and that seems to be like a light dark cycles. And we discovered that in that situation, that micro G accelerate the metabolism. Why? Well, we are still doing tests, but the point is micro G accelerate the metabolism, and they take the nutrients and the pollutants from the water very, very much fast. And also, they reproducible. So this reactor actually produce, in some situation, 45% more biomass than the regular reactor that you use. And definitely reduce the time that the water have to be inside the reactor in order to be cleaned. So reduce the hydraulic rotation time. So that's a very, very efficient thing. So this increase of the proportion of biofilm against planktonic cells in the reactor are very, very useful for industrial purposes. The other innovation that we work in, and we just patented that like, I don't know, like a year ago, is this thermal reactor, which is a sequential reactor that do 4 different processes of thermal processing the biomass. And then this reactor was designed especially to take the biomass with more than 90% of humidity, which means it's almost like a soup of micro G. So this bioreactor can take the biomass in that state and generate directly synthesis gas, biofuel, and biochar without use, no centrifugation, no drying, no extrusion, and at the end, not energy consumption. So this is like a big deal for us. And I will explain that why before. And it's because we think that the future of this treatment of the residential wastewater is the circular economy. And we really believe that micro G are the key point of this circular economy with wastewater, domestic wastewater. Let me explain quickly what happened in a wastewater treatment plant when you try to be more sustainable. This is a regular wastewater treatment plant, which biogas production and biogas combustion to try to recover some of the energy that the plant consume. The ROI is the energy return of investment, and it's an indicator of the energy balance of the plant. A ROI of 0.3 means that this plant consumes more energy that they produce. So even using the biogas, burning the biogas to produce energy, the wastewater treatment plants just get 0.38. And this is the state of art regular now in our main cities. You can improve that on Phycoremediation. Yes, you can put microalgae here, microalgae, and you can use that microalgae to increase the biogas production, and that increase the energy production. And you can take the carbon dioxide and put inside the microalgae to do even better. Yes, it will get better. ROI will change to 1.01. That means that this plant even doesn't need energy input to work. It's neutral. That's good. Yes, that's extremely good. That's sustainable, but that's not enough. You know why? Because the market doesn't like to be neutral. The market, this plant depends still from charging, from cleaning the wastewater. And the reality is that we clean the wastewater like 20% of the times because it's like an obligation or something. But the market doesn't like to clean wastewater. The market like to make money. So we understand that we have to reach that point in order to allow to make money. And this is what we are focused on. Superalgae state was a term proposed by Menger and Krug in 2012. And superalgae state says something with three principles. You have to produce more than 25 milligrams per square meter per day of microalgal biomass. And you have to reach more than 80% of recovery of that biomass, But also, you have to transform more than 80% of the biomass recovered into energy. Only then you will get to a ROI of a 2.1 to 2.4, even more. And that means that you transform the before wastewater treatment plant in an energy generation plant. And we think that we reached that point with the innovation that I already tell you. Why? Because we are reaching more than 90% of use of biomass. This is the reactor, the BF Plus, that I already told you. This reactor allows us to produce more than 25 milligram per square meter today. And we mostly use that in the second reactor to produce syngas, and that syngas to go to income, to energy, sorry. But also the residual biomass we are recirculating to the new, that we are still working on, but new methanogenic reactor, which is specialized in digest this biomass. We are even controlling the bacteria present here with biological control using phage virus directed to the other bacteria, filamentous bacteria, or bacteria that can't digest pentose. And we are sustaining a population here, the bacteria that produce more than 30% of the biogas that produce other biogas reactor. Also, more methane than carbon dioxide. We wash that biogas with the algal reactor, and then we put that biogas directly in the turbine to produce energy. So this is, you can say, new. Well, it's not so new. Many people has been working on this, but fortunately, we achieved this point, and we are now ready to deploy to the world. And the end, I promise I will not talk anymore. But the end thing is all these innovations are directed or in the context of the awareness of the Phycosphere. And the Phycosphere is extremely important for us because we discovered that without the Phycosphere, the power of the contamination of micro-G decreased dramatically. So we know now that the Phycosphere is like a very, very small space that is the region immediately surrounding the micro-G, and the concentration of molecules there, the concentration, the distribution and the type of bacteria that are there in the Phycosphere are different from the rest of the media. And this is extremely important. We find that many works are describing how the bacteria and the micro-G work together or fight inside the Phycosphere. So we understand now that our work is to allow or to promote the condition in which our micro-Gs works better with the surrounding bacteria inside the Phycosphere. So our goal in our reactors, in our process, is to maintain healthy that Phycosphere and maintain that Phycosphere helping us to our goals in the process. And that was very clear. Almost the literature already connect the Phycosphere microbiota and the change in the Phycosphere microbiota, which is a microcosmos, microscopic cosmos, with an ecological, ecosystem level process, even in the oceans, which is the huge ecosystem. The change in that phycosphere can produce, for example, change in the rain intensity, if you say it. And we basically understand this very clearly. Remember that I say that I take a Senedesmus dimorphos from the petrochemical pilot that works very well, downloading the pollutants in the effluent, and then I try to understand if that Senedesmus was able to cut the phenol ring and eat it, basically. And then I take the Senedesmus was with a chlorococcus, and then I separate the two microalgae, and I begin to do like electron microscopy and regular microscopy with tinction, and I find a bunch of bacteria. You can see here my Senedesmus and with a lot of bacteria. Then I culture the bacteria, and I just can culture 3 bacteria. Only three morphotypes. And then I sequence the bacteria, and I find Pseudomonas putida. And I say like, oh, this is very easy. This is very easy. Pseudomonas putida, we already know that Pseudomonas putida can break down phenol and all other substance, oil derived. But the point was I can find the monooxygenase or deoxygenase inside the genome of Pseudomonas putida. And even more, I do the work. I mean, I put the Pseudomonas putida in culture with the phenol, and they can remove the phenol from the media. When I put the Senedesmus with supposedly the 3 Pseudomonas putida, the phenol was removed very easily, very quickly. So what was the answer? Well, we already still don't know. We're trying to ensembling the Senedesmus dimorphos genome, but still a very, very bad draft, because, I mean, the pandemic came and I have to stop the sequences exercise. But look this. I applied this tool, BusyB, to study my metagenome that is supposed to be 1 microalgae and 3 Pseudomonas putida. And look this. This is in my supposedly easy consortia with 1 microalgae and 3 bacteria. This is much more diversity, like amazingly. We suppose that these green sequences that are the most are the genome of the microalgae, because it's a gigantic genome. Yeah, have to be a gigantic genome, because I say that I will assemble it for my PhD, then can be a small genome. Have to be a gigantic genome. But the point is, the other colors and the other genera are a lot more than just 3 bacteria, and I didn't know it. So the take over here is like we are still beginning to understand the complexity of the diversity in just 1 microalgae phycosphere. Imagine how it could be in a 10 microalgae consortia with I don't know how many genera of bacteria and fungus. And we really believe that our understanding of this correlation, mutualistic and competition relationship will allow us to improve microalgal biotechnology and make it really useful for fields and industrial large-scale applications. So that was my presentation. I hope you enjoy, and I now will invite you to make any question you have, if you have. Was almost 1 hour.
Yeah, yes, sir. Thank you, sir. Thank you so much for very informative lecture on phycoremediation of waste. Dear participants, if you have any queries, you can directly interact with Dr. Jaime now.
So Dr. Jaime, that was excellent. I've been listening to you, but it's a long talk. This is the first time I'm listening. Excellent. You improved in English a lot, I've been following you for several years. Lot. Excellent.
Thank you, Doctor. It's a big honor for me that you say that. Always, I learn from you.
Because I've been with you throughout, so I know.
Yes, sir.
Excellent.
Really, it's great to hear, sir, because being a medical doctor, he's doing wonders with human and the other biota also. Really,
yeah, he's an MBBS MD in trauma care.
Yeah, really very happy.
Yeah.
Yeah,
well,
my
girlfriend say that now the patient is the planet, and I still a doctor, but now the patient is not human. It's the enormous planet that we have.
That's the patient. For the environmentalist, the Earth is the patient. Definitely.
Yeah.
And if you go to other planets, the entire universe will be the patient.
I think that we are too old for that.
That is good.
That's for our grandsons.
Okay. Any question?
Dr. Jaime, this is Dr. Ashok from MKU Madurai. I need some clarification.
Sorry.
It was an excellent presentation with real field trials. I'm happy to see that. Meantime, there are a variety of microalgal species have been used for this bioremediation purposes. But before choosing them, we are paying much attention whether they do have a short span of doubling time, and how best they can utilize the nitrate, phosphate, this and that. We are looking at. Meantime, have you ever looked into whether that microalgae has a potential to produce any kind of toxins? Because when we use such a microalgal strains for these bioremediation purposes, once after their utilization, they will still remain in that environment. Whether will they pose any serious threat to the environment by producing toxins? Have you looked into that aspect with the isolate whatever you have?
Yes. And in the case of the reservoir, we have to check the cyanotoxin, the microcystin, by molecular method, ELISA, with a special kit for that. And we confirm that the microcystin presence was decreased, because that was the problem. In other cases, if we don't find in the microscope, we have a very good phycologist here that is a student of Dr. Siva Subramanian. He's teaching her to identify all the species, and then when we find some cellular evidence at the microscope that could be the cyanobacteria at the water, then we need to test. If not, we don't do it. If we don't find like a macroscopic evidence that could suggest that will be microtoxins there, we don't do it because the test is extremely expensive, and then we have a very restricted budget here.
Thank you.
Can I?
Yeah, Arvind. Yeah.
Very nice presentation, sir. I would like to ask some questions. One of them it was already raised by my guide, and my question is: you have successfully demonstrated a field implementation of the bioremediation. So, what will be the overall cost to make the implementation? And you have gained some energy and resources from the bioremediation system. Does it profitable?
Well, we already. How can I say this? Remember the chart that I told you would compare the cubic meter treatment with the other technologies. This is very clear. We cost like 10% of we spend a 10% of the energy that the other methodologies spend. Yeah, we have for example a good story about that. The first time that Dr. Shiva came to Colombia, so we was at the oil field. And they didn't install us a transformer because the other pilot plants use so much energy that they have like these size connections, and we can use that. We need slow down the energy. I'm not engineer, electrical engineer. I don't understand that. The point was, Dr. Shiva arrives, and we was there, and the plant have no energy. So what we do? Say like, oh my God, these engineers of the oil company was so slow. We can't have Dr. Shiva look in the sky. We need to work. And my engineer connect the entire power plant to the light of the field. I mean, that was like we use like an air condition, totally consumption of energy of all the plant. The surprise was so big for the oil company engineers when he arrived and he say like, "You're working." Say like, "Yes, we need to work." Our expert comes from India. They say like, "How you do?" And we say like, "We connect to this." And of course, so that was like a big fault. You know, we can be like have a consequence. But they was so surprised that all our plant works with the same energy of the bulb or the light that they say nothing. They say like, okay, you do that. But the point where I'm trying to fix is amazing how much less energy we use compared with other methodologies. Like that allows us to operate in very like far away places that other companies can go. I don't know if that was your question.
And okay, that's nice. Okay, another question is, in India, the sewage water not only contains an organic material, it also contains some chemicals and phenolics due to the domestic usage. So it will be very hard to make a successful implementation in India, and moreover, some toxic materials also will be present in the sewage treatment. So by your experience, what will be your suggestion, whether the bioremediation through the bacteria or bioremediation by the algae? Because the natural bacterial augmentation, it will be easily happen in the wastewater as compared with the algae. So what is your thoughts in this part?
Well, when we patent the Biopore plant, is the union of three main reactors, and the first one is bacterial.
Oh.
And then usually with the complex wastewaters, because this is true. I mean, in some countries, the regulation doesn't allow to the industries to put their effluent in the sewage system. But in all countries, you know, the industries also don't follow the rules and put the chemicals inside the sewage systems. And then the chemicals arrive to your plant and you have to do something. So we combine bacterial anaerobic treatment, but with a special configuration that I can't talk totally now, but this is a special configuration that made that system stronger than the regular ones. So, but we feed that bacterial anaerobic system with microalgae, because we discovered that increased almost 30% the methane production. So, but this is another thing. You know that the microalgae are extremely good cannibals? They are good cannibals because when you use the digestate of the anaerobic treatment to feed the microalgal reactor, the growing increase like crazy. So I say like, well, if they are cannibals, who I am to discuss? I will give like part of microalgae to feed them. And then we have like increase in the biomass. Also, because we use the combustion gases and we use the reactor to wash that gases, what we're doing is like taking the carbon dioxide in order to increase the proportion of methane. So the answer is, for us, the best answer was to have both systems. In some cases, we can bypass the bacterial and go first to the microalgal and then come back to the bacterial. I mean, we made a lot of configuration according to the concentration of the wastewater, because are different. You know, the only problem that I find that is like our kryptonite for Superman, you know, are the pharmaceutical wastewater, because they have a lot of antibiotics there that also are algicides. So you have to make like a very good analysis of that water, because that could kill everything in your reactor, pharmaceutical.
Thank you so much, sir.
Sir,
No,
I have
you
a
I think there is small confusion. The title is sewage. That doesn't mean it's only domestic sewage. Dr. Jaime refers to all wastewater. He says sewage. So don't mistake it.
Yeah.
In India,
We
it's
like
sewage, only
sewage.
domestic sewage.
We like sewage because sewage is the most abundant wastewater in the world. So if you can connect the sewage with the energy production, then you are connecting two things that are the main problem with humanity, because more people, more sewage, and more energy demand. So now you have the sewage that produce energy. So you connect that, and also you connect that with carbon capture. So imagine the potential. Imagine the potential if India implements something like that in the 30% of the sewage, total sewage. That will make a difference in the balance of carbon in the atmosphere. I'm sure of that. If you put India and put China, imagine. So we are so happy because this is working. And actually, it's not just working in the cleaning. I mean, the cleaning thing. It's working financially. You know, we used to say that with Phicor, the wastewater is money. And nobody dropped his money to a river. So we are giving the market a reason to implement this in order to can save the planet, or try at least.
Yes, sir. Sir, this is Varlakshmi, Dr. Varlakshmi. Actually, I have a question. Sir, while you are employing microalgae consortia along with bacteria, what was the time requirement needed for microalgae consortia alone and microalgae in combination with bacteria? Which one is more efficient and which one is requiring less time for doing this bioremediation?
Yes, we have like between 30 to 45% reduction in hydraulic rotation times. So we can move the water faster, you know, when we use the consortia. When we began to understand that we always like handle the plant for the microalgae, like ignoring other microorganisms. But when we make lab tests in which we retire we have another project and we were trying to do something crazy, and then we were producing protoplast. What means do you retire the wall of the microalgae? And then we discover that the problem was not the wall. The microalgae regenerate the wall, but not the bacteria. And then the microalgae get so weak that I can't believe it. So we say like, no, wait a minute. We have to characterize our consortia, having in common the bacteria also. And we have to try to give the conditions to the bacteria also grow with the microalgae, not all the bacteria. And the nice part is that the test that you do in the lab with the effluent made the selection. You know, all the microalgae will die, and only the microalgae that survive. So you take them from several flasks and you make a mixture, and then you do like the second part of the sensibility test, and then that make the selection, and then you scale up. How many time takes that? I will say like probably a month and a half, something like that. You know, then you begin to scale up in the lab. So the last discovery was that the micronutrients, the phytohormones, are very important. You know, so now in that project in Sucre, we use enormous quantities of microalgae, but that's not necessary anymore because Dr. Silva Subramanian is very clever and he find the proper mixture of that. Then you have to use so many or some less volume of
what we call as Phycoplus technology.
Phycoplus, yeah.
That
was, the change is amazing. And then you don't have to spend month and a half. You can spend 3 weeks because you will scale up not to 10,000 gallons per day, but it's just a cubic meter or something like that.
Yes,
You can imagine how hard it is to produce 10,000 gallons in the middle of nothing. I mean, like without electricity, like it's a headache. I will use another expression, but let's say headache.
Yes, sir. Sir, have you ever employed any epiphytic bacteria?
What?
Epiphytic bacteria of microalgae. Means the
No.
bacteria which is grown on microalgae. Yeah.
No, actually, what you're trying to say is we don't isolate bacteria and then try to mix. The
Okay.
bacteria are already symbiotically growing in each algae. In fact, recently we did an work with a British counterpart.
Yeah.
Dr. has published a paper. We gave chlorella and sanitous mist. They isolated hundreds of bacteria isolated by symbiotic from each, and they are different. I mean, the domination in one chlorella is different. Domination in sanitous mist is different. So if we mix all this, chlorophyta, all the algae, you are mixing huge amount of symbiotic bacteria, which you don't need to bother. You don't need to work, study, and all that. There is a problem only.
Yeah.
Otherwise, we don't mix any bacteria with. But we did this in Tata Steel. We did this
Yes.
mixing in Tata Steel. But here we don't do it because we mix the algal mixture. We also mix thousands and thousands of symbiotic beneficial bacteria. You don't need to bother. They are already there. We are
Yes.
not using any axinic culture anywhere. It's all
Okay.
bacteria.
Yes.
Right.
But what we are doing is to sequence, to identify, and to try to understand. For example, we are doing studies now about the abundance and the I forgot the word. Well,
I was surprised about your English. Very, very good improvement there, Dr.
oh, thank you, doctor.
Otherwise, we'll be mixing a lot of Spanish words.
Yes. I just do like 3 times on that.
Now you are much better.
Thank you. The abundance and the, well, how is that name? Don't matter. When we begin a process, we take a sample, we extract the DNA, and we find
Metagenome analysis, sir.
genome,
Yeah.
and then genomics, and then when the process is like very established, we do another to try to understand if there was like 100 bacteria at the beginning and just 20, or different. And when wastewater, with domestic wastewater, it's very interesting because domestic wastewater have a lot of bacteria. They will change your composition of your consortia, and that's what we're trying to understand now. But Dr. Shiva Subramanian is totally correct. We never take a bacteria to add to the consortia because the microalgae made that selection in natural way.
Yeah.
We were trying to find what is happening.
Thank you, sir.
Diversity is the word.
Yeah.
Diversity. We're studying the diversity of the consortia at the beginning and at the end, at the middle. That's why we call that predominant microalgae microbial consortia. And we say predominant microalgae because we understand that the microalgae is like the very basis, like the rock over the other build their houses.
Thank you, sir. One of our student, she has some question. Chandrani, are you there?
Yes, ma'am.
Yeah, you can ask now.
Yes, sir. Greetings, sir. I had a question on nuclear waste affecting the phycoremediation process. Does it affect the success of the phycoremediation process, the nuclear wastes?
I don't understand the word, sorry.
No, he's talking about nuclear waste, atomic, nuclear.
Atomic?
No, the atomic power plant, they send out a lot of waste with nuclear waste.
Oh, well, like radiation.
Radiation. I think we are not done yet.
Well, the radiation affects every organism that have DNA, because that will create like mistakes in DNAs, but will damage the DNAs of the organism. I really don't know if the microalgae, because have the wall, can't like be less effective for radiation than other bacteria, for example, probably less affected. But if radiation is too high, I mean, you have to find the tolerance of the organism. And the best way is to try to find if in the place where the radiation is happening, there are already microalgae. If there are microalgae there, probably that microalgae could help in a phycoremediation process, even with the radiation present.
But we have not done it.
What?
We have not done it so far.
No, we never work with that. We have no nuclear energy here in Colombia or weapons, so we have no. At least we have not that contamination process.
Very, very peaceful people.
But that's true. That's
Yes.
true, Dr. Shiva. That this is a good question. You know.
Yeah.
In fact, if you go to Colombia, everybody smiles. You know, everybody smiles. Very friendly people.
Well, not all the time. When the soccer team lose, we don't
Yes,
smile.
but I was in the Barranquilla when we Colombia lost. Last March 4th, we had we visited the stadium to visit Colombia, Brazil. Colombia lost, but nobody was shouting. I mean, you took it. You never made any shouting and all that. I was enjoying it, in fact.
Yeah, but yes, Chandrani, if you wanna know that, you have to go to the place and try to recover some specimens.
That's really interesting, sir. That was going on in my mind. Thank you for answering, sir.
No, thank you for your question.
Yeah. Is there any questions? Okay. Sir, I would like to thank you on behalf of ASM Student Chapter Series as a faculty advisor of ASM. I wish to invite Mr. Gunasilan, Vice President of this Student Chapter. He is a PhD scholar. He will be delivering the vote of thanks. And before that, I would share a few words. I would like to thank our great Professor, Dr. Sivasubramaniam sir, who has given your address and details to contact you for this great occasion. Really, your talk was very much interesting and very much useful for me and my students also. And here, the participants, not only from our university, all over the country, they have participated, sir, and they have enjoyed your session really. It was admirable one, sir. Thank you so much. And we'll be contacting you in this bioremediation aspect in future also. So please do help us. Whenever you are free, at that time only we can make a call. Otherwise, you are very busy. I'm really sorry.
And make a visit to India very soon.
Yeah.
I will be there.
Please
I
tell
have
you.
to go soon. Yes, that's true. I hope.
We can make, sir. Yeah. Thank you, sir.
Okay.
Thank you so much to Dr.
No,
Jaime.
thank you for inviting me. Thank you for inviting me and for being so receptive to my few knowledge that I get about this field.
Yeah, you both are real-time demonstrators, sir. Really, you are the gift for the earth. I would say like that. Yeah, thank you so much, sir. Thank you so much.
It is good that you have come out of medicine.
Yes.
But now you are treating COVID patient. I think you are become a doctor right now.
Yeah.
That's why you are.
This is a passion. I remember the time when Dr. Sivasubramaniam invited me to become a green warrior, and I say like that's for real. But this is real, and I think that we can make a difference. So I invite all the student presence and also the professor that continue working in this field. If there is a field that can make a difference for the world in the next years, it is microalgae. So continue working. Don't surrender. It's hard sometimes. Don't promise that you will assemble a genome for your PhD. Don't do that. But the point is, you can work and you can contribute in this field. And this is a very, very, very beautiful field.
Yes, sir. So one of our student, she raised a question to you. I will read the question. Sir, do you have any experience on plastic degradation by using microalgae?
No, not at all.
Okay.
That will, but the plastic degradation is something like science, and yeah, is a field that I never try until now.
Okay. Shalakshi, have you got it? Yeah.
I'm sorry, I can hear. Sorry.
Yeah.
So,
your question was.
sorry, can you repeat it?
Yeah. Did you get the answer from Dr. Jaime?
I'm very sorry, it wasn't audible.
Oh, okay. I will let you know soon.
Okay, thank you, ma'am.
Yeah. Guna?
Yes, ma'am. Yes, ma'am.
Yeah,
Yes, ma'am.
you can propose the vote of thanks.
Thank you, ma'am. On behalf of ASM Student Chapter, I take this opportunity to propose vote of thanks. At the outset, I thank our speaker, Dr. Jaime, who took out valuable time from his received schedule, gracious, to share his valuable knowledge about bioremediation using algae, which is the need of our due to our growing environmental pollution. And special thanks to Dr. Varalakshmi for organizing this great ASM Student Chapter series from 2019 onwards. And I would also like to express my thanks and gratitude to Dr. Shiva Subramanian and Dr. Ashok Kumar sir and all esteemed delegates of the webinar for their presence. Finally, the wonderful students and scholars who have turned up for this, turned up in good numbers, not only from our school, from other universities also. Thank you. Once again, I thank all for your cordial cooperation. Thank you. And dear participants, please fill the attendance and feedback form. The link is attached in the chat box. Thank you. Thank you very much.
Thank you, sir. Thank you, Dr. Jaime. And thank you, Shiva Subramanian, sir. Thanks a lot. You are always supporting me. Thank you, sir. Thank you, sir. Yeah, thanks.
Thank you very much.
Thank you.
Have a nice day. It is almost midnight for you.
This is 12:34 here at the middle of the night.
Monday. You are still in Monday.
No, yeah, I'm Tuesday now. 35 minutes.
Oh yes. Okay.
So we are. I'm not anymore in the past.
Yes, you are the present.
I am the present.
Okay,
Thank you very much to all
Good night.
for your attention and your
Good night.
interest.
Yeah, thank you, sir. Thank you so much.
Goodbye.